Okay, well, welcome back, everybody. So, as you hopefully remember, last week we were talking about faster path search algorithms for milestone 3. Let me shrink that down so I can see the chat. Yeah, let's see, there we go. Okay, so we're talking about faster heuristics for solving the shortest path problem. Okay, so we saw that Dijkstra's algorithm is pretty efficient, and but it does explore somewhat in the wrong direction. And that wastes some time. So we saw, well, what if we did what's called either an Astar or best first search? So we want to basically look at the most promising partial solutions, the most promising search directions first, and hopefully, therefore, we'll find the destination without looking at so much of our graph, and we'll save CPU time. And we saw that a way we can do that is basically to go from breadth first search to Dijkstra, we just changed how we're sorting our wavefront. And to go to Astar or best first searches, we are going to just keep doing that. We're not going to change anything. We're not very much about our algorithm at all from Dijkstra's. We're just going to change how we sort the wavefront. Okay, so what's the idea? So let me make this full screen. Oops. Let's see. Okay, so we're at some source. So we know where we started, and we've already done some exploration in our graph search. So we found certain nodes that I'm showing you here, and what's in our wavefront now are these two nodes. Okay, so the two circled nodes are what are in our wavefront. Let's call them node 1 and node 2. And the way our search algorithm works, our Dijkstra's algorithm works, we know what the best time is to both of those nodes because we've been searching outward in this wavefront. So we've reached node 1, and we know that the best time did has been 40 seconds. And we've also reached node 2, and we know that the best time did has been 45 seconds. So let's go for first, let's just do a skill testing question. For Dijkstra's algorithm, which of these nodes are we going to look at first, right? So our wavefront, we're going to take something out of the wavefront and decide to look at its neighbors. Which of these nodes would Dijkstra's algorithm take? Yeah, so Dijkstra is going to take N1 out. It just sorts the wavefront by the smallest travel time to any node in the wavefront. So it's going to look at N1. But we can look at N1 and we can see, well, N1 is actually a long way away from the destination. Here's our destination way over here. Doesn't seem very likely that N1 is actually, this path that has gone here so far is actually going to lead us to the best solution to the destination. So it seems likely that we're going to waste some CPU time. So we don't want to look at N1. We would be better off to look at N2 first. So how can we do that? What can we do? We're going to change how we sort our wavefront. Okay, so we want to look at N2 next. What could we do to make that happen? So any ideas? If you got any ideas, just unmute yourself or type them in the chat.
How about we have we can say instead of sorting by the costs, we can have the cost, but also an estimate of the cost to the destination. So instead of saying sort by the cost I've seen, sort by what I expect the total cost to be, where my estimate, the distance over max speed or something like that.
Okay, so that's a good idea. In fact, that's a very good idea. So basically, you want to sort by an estimate of total cost. And you actually gave a very good idea for that. So, but before I go for, so your idea was basically let's estimate how much travel time is left to the destination. Is that the idea? And then basically add that. I know some travel time, 45 seconds, and I could estimate the travel time to the destination. And I can estimate that reasonably well because I know I'm in a street map and I actually know where I am. Okay, so I could come up with estimates of that travel time and add them together, and that's actually a very good way to do it. I see some other ideas in the chat, so let me talk about those as well. So there are other ones like maybe let's use Euclidean distance, and that's actually a common one. People try a lot. So let's say that we're going to do some combination of the time to N2, or maybe let's just sort by distance. Let's just sort them by what is the distance to the destination. That seems reasonable, but it's dangerous. Okay, if I just sorted by the distance to the destination, then I would never backtrack. I'd only keep going forward, and I could get into problems because I might find that there's a lot of blockages and I have to detour around a lot out here. And maybe it turns out, and maybe there's a highway over here. Okay, so maybe the 401 is right around here. So it actually turns out that because I had to detour around a lot as I went through various nodes in this direction, maybe this one was 50 seconds, maybe this one was then 60, maybe this one was 70. I still haven't reached my destination. And let's say that the 401 is right here. So it actually turns out that in 30 seconds, I could actually surprisingly get all the way here. I need to make sure I will backtrack and look at this if it turns out that the search is not going so well. So if I sorted by distance, I wouldn't do that, right? I would basically add the distance to this point plus the distance to the destination, and I basically won't backtrack. So that would be too aggressive. I could try to have some function that combines maybe distance and time in some way. So maybe but it's hard to have a sorting function that is kind of combining two very different things. So what Isidore suggested, now I see some people commenting on as well in the chat, is yeah, let's try to get the total travel time. So the total cost in this time is total travel time. So we want to estimate that. And we want to sort on that. And we can estimate very quickly what is our travel time to the destination by taking the Euclidean distance. We know that we're going to at least travel that far, and dividing by some estimate of the speed limit. Okay, so time to destination, we can quickly compute Euclidean distance divided by some speed estimate. And the nice thing about that is, well, now we have something with the same units. We have time to the node we're at, and we have an estimate of time to destination. We can add those two things together, and we know what it means. It's an estimate of the total time. Okay, so and we can also compute it quickly. So what you want in an A-star, this estimate is called the heuristic in the A-star literature. So we don't know it's correct. It's a guess of how much more cost, or in this case, time, is going to come in the future. And you want to be able to compute that quickly, because otherwise, well, you could slow your algorithm down by taking forever computing this sorting function. But Euclidean distance, we can compute very quickly because we actually know exactly where this node is. We know exactly where that node is. So it's an order one computation to figure out what's the distance between them. Now, what about the speed estimate? Speed estimate's harder. I mean, that's a function of all the roads that are in between the source and the destination. So it's a lot harder for me to estimate the speed limit. Okay, so what do you think? Okay, so the distance is easy. Speed estimate, a bit harder. Okay, and I just have this is another blank line for me to write notes on. Yeah, so see in the chat, so kind of reasonable things you could do here, because we want it to be fast, is I could basically take maybe the average speed. So I could compute the average speed in the city. You know, that might be the best guess that I can make. I see people saying, well, maybe we should use the maximum speed anywhere in the city. And this seems reasonable using the average speed. That would actually give us the best estimate of the time less to the destination. But we have a problem of it's not an underestimate. And in milestone 3, we want you to get very good paths. Okay, I want you to get paths with travel time as short as Dijkstra's algorithm would find, which means that if there's no turn penalty, they're optimal. If there's a turn penalty, they're close to optimal. And if you use the average speed, it means that there's a chance that because you say, well, the average speed to get here, maybe that's 50 kilometers an hour. Okay, so maybe I guess that if I have 50 kilometers an hour and there's a road that goes straight here, that the time that I'm going to take in the future is, let's say it's another 50 seconds. Okay, so I would say there's a 45 seconds known time, there's a 50-second estimate in the future. So the total estimate of time for N2 would be 95 seconds. And the total estimate for N1 would be much higher. right? So this estimate would be, if this was an estimate of 50 seconds, then this estimate is probably 110 seconds maybe. So this one, the total, so that's maybe my estimated time, and my total time might be 150 seconds total estimate. So that's just adding the known time plus my estimate of the future time. But because I use the average speed limit, this isn't a lower bound. Maybe there is a 401 highway right here. And it turns out that, in fact, I can do this in, let's say, I said before 30 seconds. Okay, it's really fast. Maybe 30 seconds is a little too fast. Let's change that to 40. So let's say I can do, there's a freeway that lets me get there in 40 seconds. So in fact, 40 plus 40, I could get here in 80 seconds. There's some path that exists with that time. But I'll never look at it. This one looks better, this N2. And as I keep going towards the destination, I'll keep estimating my time, and maybe my prediction was pretty good. There's a bunch of local roads, so at each of these, I keep predicting the time is around 95 seconds. There's less time to the destination, but there's more time that's known, the best time to this node. So basically, I continue finding I'm on track to reach a 95-second solution, and I follow this path, and I say that's my answer. And I'll never go and explore this other option, which actually seemed less promising, but actually led to a better path. Okay, so yeah, you need your estimate of the future travel time to be a lower bound. Okay, and in the literature for Astar, that's called an admissible heuristic. If you want to guarantee that your answers are optimal, then you need to make sure that your estimate of the future cost, or in our case, the future travel time, is a lower bound. Dijkstra's algorithm. So Dijkstra's algorithm can be considered, whoops, that's misspelling Dijkstra. So basically Dijkstra's algorithm, the future estimate is 0. Okay, so you can think of Dijkstra as a special case of an A-star algorithm where you just guess that there's no cost or travel time in the future. And that's clearly a lower bound, right? We're never going to get a time that is less than 0. So A-star algorithms basically get a better, or basically less optimistic, guess of future cost. And again, in our case, future cost is time, travel time. And what that does, and that makes them more efficient, right? If you use an extremely conservative estimate of the future travel time, like 0, you actually devolve to Dijkstra's algorithm. It's correct, but it's no faster. If you use too aggressive an estimate, like your estimate is not a lower bound, then you actually risk not finding the best path sometimes. Okay. Now, in some cases, I told you that in integrated circuit design, we actually use path search heuristics in the CAD tools that are used to wire together things in FPGAs and in custom chips. And those are actually shortest path algorithms. In those cases, you don't worry about getting a lower bound. So if you're willing to give up optimality, you're willing to risk that sometimes you won't find the shortest path, you can make another class of algorithms called directed search algorithms. Those ones do not guarantee that this estimate of what will happen in the future is a lower bound, and therefore they give up optimality. But they can be significantly faster because they don't have to use a lower bound estimate. Future cost or heuristic estimate. Okay, so when you need really fast path search, you can move to those kinds of algorithms. You should not do that. Okay, don't do for M3. The reason is you don't need to. You don't need to make your path search that fast, and we want it to get the optimal answers. So if you did this, you're going to fail some of the tests. You'll be unhappy. Okay, so you're going to stop. Don't go any further than A-star. Dijkstra's is a good algorithm. A-star is not much extra code. It's a bit faster still. But I'm just passing on that There's another class of algorithms beyond that that's faster, but doesn't guarantee optimality. It's again not much difference in code. It just changes what is the estimate of the future cost. Okay, I see. Are there various questions in the chat? Is there a way to iteratively improve a suboptimal path, like do a directed search and then improve it? It's a good question. There's actually a lot of literature when you get into these kind of algorithms. Well, both Astar and directed search. It's not obvious how to find a suboptimal path and improve it, but there's a lot of literature, so I can't say that nobody's done that. Okay, so that's the idea of an Astar implementation. And maybe you can come up with a better heuristic or future cost estimate. Just make sure that it's a lower bound. If you do, your algorithm will be even faster. Okay, so what are we doing in the Astar implementation? So I'm going to just tell you something that I often see students do incorrectly in the lab. So we're changing the wavefront sorting. We are not changing the best time that has been found to some node from the source. Okay, the best time, remember, we're using it to decide, is this the best path we've ever seen to a certain node, or have we already seen better paths? So we need this best time, the kind of known cost to get here so far, to be accurate. Otherwise, we wouldn't know when we found a better path to a node. So we want to keep track of both things. You want to know, essentially, this is the known cost or best time from the source to me, and then there's an estimate of what's going to happen in the future. And don't mix those two things together in one variable. So a good way to do this is this wavefront, the data we're putting on it keeps getting a little more complicated. So here's a new data structure that we could use, wave element A star. So we still have to have a pointer to a node so we can look up information about our intersections, or if you want, you could use an integer ID. Given how you've set up most of your data structures in milestone 1, an integer node ID may in fact be more convenient, so that's fine. We have an edge ID of how we got there, so we had that before. We have a travel time, which is the known time to get here. And I know that for sure. That's all the time I've had so far in all my predecessors to get here. And then we're going to have another member variable that is, what am I going to sort on? Okay. And I guess what I'm highlighting is I'm separating these two things. I want to keep track of what is my known time that there's no ambiguity about to this node. And then I have a separate variable storing, this is my guess of the total time that it's going to take me to get to the destination. And that's what I'm going to sort on. When I take things off of the wavefront, this travel time, which is my known time, is what I'm going to use to compare to the best time to a node to see should I update it. Okay, so keep those two things separate. Let's see, I see a question from Daniel. Let's see, not sure why the sorting order has to be an underestimate. All we need is the stopping criterion to be an underestimate. Let's see. I think I need to think about that question afterwards. So you can have a lot of bad things happen that are relatively subtle if your estimate to the destination is not an underestimate. I think you're right that if it wasn't an underestimate, but after you reached the destination, you kept searching for long enough, then you could probably still guarantee optimality. So there's probably another way you could do it in that case. So I think you're right, but I think you'll sacrifice CPU time by doing that as well. And it's more complicated to code because you can now use a more aggressive estimate. But once you reach your destination, you still can't stop searching. You're going to have to go search. You have to keep pulling things off the wavefront. Whereas if you code with an estimate that's lower bound, once you find your destination, you know that that's the best answer when you pull it off the wavefront. Okay? So let me quickly demo this. All right, let's see. Blow this up a bit. Okay, so we've gone through a few different path search algorithms, and I've selected over here Dijkstra. So you saw that last week, but let's just click on this again. And I slowed down the graphics a bit so you can see it more. So the starting point was over here. My destination is over here, and it's kind of searching outwards in circles. So you can see it's pausing once in a while due to Zoom just buffering. But you can see it's kind of searching outwards in essentially a circle in the whole graph. And I've slowed down the graphics, so it's going to take a little while. It's almost found my destination. So hopefully soon it does that. Okay, so I found my travel time. So it's that red path. So let me change this to A star now. Okay, and now I'm going to find a travel path from here to, let's say, over here. Okay, and you can see it really liked following in the right direction. It kind of followed the highway and went in the correct direction, didn't backtrack much at all. So let me do it again. Okay, so I'm going over this way. Actually, that one was hard to see. Let's do another one over here. So you can see it's pretty directed. It finds the highway and it tends to follow that highway and then look around there. So it doesn't do very much backtracking. So we're saving quite a bit of time. So it doesn't go exactly to the right spot without any searching elsewhere, but it's much reduced versus Dijkstra. Okay. Let's see. So let me go back to the slides here. Okay, so any questions about that algorithmically? Okay, looks like lots of discussion, but don't see any questions. Okay. Okay, so let me give you some tips on performance tuning and debugging for milestone 3. So the amount of code you have to write for this algorithm is not that much. The challenge is often that you're just moving a lot of data, so it can be a bit more tricky to. Whoops, let me get rid of this. I'm on the wrong machine. So it can be a bit more tricky to debug. So let me give you some tips on that. So there are lots of tests. So this is the milestone 3 test report for a reference solution, and you can see there are 30 separate tests. Now they overlap a lot. We create a lot of public tests, so you can kind of see how are things going. So what's your strategy? You're going to start off. You're going to fail lots of tests. You can see that we're testing on multiple maps. Okay, so we're testing on Interlaken, we're testing on Toronto, we're testing on London. So these tests are kind of follow the same style, but we're just testing on multiple cities to make sure you're robust across cities. So each of them follow the same kind of grouping. There's a path cost test. Okay, so the path cost for Interlaken, Toronto, London. So path cost is just checking your simple helper function that takes a vector of street segments and returns what's the total travel time to go from the start of the first street segment to the end of the last one. So that's not a very difficult function, but you want to make sure you pass these tests first, because that's checking did you compute turn times properly and so on. So it's to help you get your underlying code correct. Next, we have tests that are called simple legality. Okay, so again, I see them in 3 different cities. So these are testing, did you get a legal path? Okay, so you said that you started at a certain intersection. We want you to go from some intersection to another intersection. Did you actually get there with a sequence of street segments that are actually connected, and you didn't try to go, if this was one way, it's going in the right direction and so on. Okay, so it doesn't check is it optimal in any way. So you could meander around some. It just checks, is it legal? And these simple ones are for nearby intersections. So it might ask you to go, 1 or 2 intersections over, but they're not going to go over the whole map. So you want to pass those, because if something goes wrong, these are a lot easier to debug because not nearly as much data is moving around. Okay, then we get into the next set of tests, which are legality. Okay, so there's one for each of these cities. Legality is basically, now I'm going to give you a couple of intersections that are farther apart. So here and here, so you might need to follow a path that goes through a lot of street segments to get from one spot to the other. Okay, so they're longer paths. Are they legal? So we're still not checking whether this is the lowest travel time. We're just checking, can you in fact follow these street segments and get from the source intersection to the destination intersection. So make sure you pass those. Then we have simple optimality. So simple optimality, again, we got it for every one of the three maps, is again just these short paths. So we're back to this one. And now we're checking, did you get the fastest travel time? So now maybe there's a, whoops. So maybe there's a shorter path that goes like this. For simple optimality, we want you to find, that path. If it, or a path with that travel time. We never actually check for exact paths. We just check that your travel time is okay. There might be a lot of paths that have similar travel time, so we're not hard. All the unit tests are essentially algorithmic. They check if your path is legal, then they check if its travel time is good enough. We never check, did you get this exact path, because that wouldn't be robust. Okay, then optimality is just the same thing, but now it's for these longer paths, right? So we got a longer path, and maybe it turns out that there's some nice path to get between them. We want you to return a travel time that is, within a small percentage increase over this pretty good path that we know about. And then the last set of tests are down here. And we change the color again. So they're performance tests. So all these things with performance in their name are performance tests, and medium isn't that hard. Your code has to be not super slow, but not super fast. Hard, your code needs to be faster, and very hard is the toughest. Okay, so this is checking how good is your algorithm and how well have you coded it. Even very hard, it's actually 2.5 times slower than our reference solution. So very hard is not, this is like an impossibly difficult task or anything. It's just you're going to need a pretty good algorithm and pretty well coded. And many people won't pass all these tests, and that's fine. This is not the reason we have so many tests. Is we're not doing binary grading, depending on how many of these tests you pass, and there are basically equivalents of these for the private tests. That is determines what your auto marked part of milestone 3 grade is. Okay, so if you go, wow, I just really can't pass a few of the very hard tests, it's not the end of the world. Okay, there are going to be lots of people who wind up in that situation. You can decide whether you really want to pass those or whether you're fine with passing most of them and you just want to move on. Let's see. And there'll also be a few corner cases that we check. Read the header file carefully. It says what to do in a couple of unusual circumstances. Make sure that your code actually does that. How much will we lose if you don't pass the very hard test? I don't have an exact number. Maybe 1 out of 8, something like that ballpark. So it's not going to be a catastrophic number. Okay. And if we find that very few people can pass very hard, we'll make it easier. That hasn't been the case in prior years. So my expectation is that there'll be a significant number of people who pass very hard. If we find that's not the case, then we'll have to go check, did we accidentally change the CPU time level? Because it shouldn't be that hard. Okay. Let's see. Anybody on the chat here passing? I mean, it's kind of, I don't think that many people have coded that much yet. To pass very hard, usually you want a reasonable A-star implementation. So that's going to be your fastest algorithm. Okay. And so, okay, so I see some people are not yet passing very hard. So keep working on it. We'll see how it goes. Okay, so I kind of told you the order in which I would attack these tests. When you're debugging algorithms, you want to start with a really simple test case. So those are basically the simple tests. Their name has simple in their name. And some of those have intersections that are right beside each other. So those ones you can actually just watch execute in the debugger. So you put a breakpoint in the debugger, you watch exactly what happens, you make sure it does what you expect. Okay, so you can use the simple test cases we've given you, or your milestone 2 UI lets you click on intersections and you can print out their IDs. So you can also use that ID UI or your milestone 3 UI to make really simple test cases. So you can use ours, you can make ones. Okay, so let's say you're now past that. And I actually really like watching my code execute in the debugger. And for a simple test case like this, I can do that. It's not going to run through loops that many times. I want to see that it does exactly what I expect so that I trust it. Okay, then I can do a slightly harder test case. So some of the test cases in those simple test cases are not right beside each other. They're 2 intersections apart. But that you can still watch through. You can still watch that go through in the debugger, and you can see that you do the right thing, you pass the test, and also nothing looks funny. So watching it run in the debugger essentially does more than checking that you actually passed the test. It also shows you did it in a pretty the way you expected. You trust the code a lot more. Okay, then you move on to the more general cases, which have names with legality in them for legal path or optimality if we want to check that the paths are fast. And those ones can be far apart. So that moves a lot more data. You can watch it execute in the debugger, but it's more difficult to watch the whole thing because it's just moving so much data that if you single step through it, you could be single stepping for a really long time. So that's why you want to watch these simple cases first. Okay. There are two kinds of tests in these more general legality and optimality test suites. We sometimes call your find path function with a turn penalty of 0, and we sometimes call it with a turn penalty that is not 0. That can be helpful in your debugging. If you find that you always pass when turn penalty is equal to 0, but you fail when turn penalty is not equal to 0, well, that's a big hint, right? Focus in on how do you handle turns? Is there anything different in your code? Anything that becomes active, any different cases you have to consider when the turn penalty is not equal to 0. So that's why we give you some cases for both. Valgrind obviously is really useful to check for memory problems. So there is a valgrind test in exercise. You want to run it often because if you've got any memory corruption issues, you want to get rid of them right away because otherwise it's really hard to reason about your program. You can't debug it. It's also a good idea to run the debug check build. It overlaps a lot with valgrind. It will check for memory problems, but it checks for another thing that valgrind won't check for, which is that the STL containers are valid. So you've already seen one of the things it does. It checks that a vector is not out of range. Okay, so if you have a vector, of int v, and let's say v only had 2 elements in it. If I access, v of 3 or v of 2, then this is going to give me an error, right? If I set that equal to something. Okay, that valgrind's going to catch that too. Okay, you'll probably get a better error message from debug check, but valgrind would catch this. Debug check, though, checks some other things on containers. So in this milestone, you're going to be using a priority queue or a heap. They're basically the same thing because the STL priority queue is built on top of a heap. There are bugs that you can introduce in your code where your heap, which has the property that the smallest element, so this is travel time, the smallest travel time, maybe it's 50 seconds. Whatever node in your wavefront has the smallest travel time is at the top, and all the nodes underneath it have larger travel times. Maybe this one's 60, maybe this one's 70, and so on through the whole heap. There are bugs that you can introduce in your code where you break this property, where you wind up getting an entry with, say, 40 seconds here. That's a bug. If you use the priority queue properly or the heap properly, this would never happen. When you run the debug check build, every time you put something in the heap or take something out of the heap, it actually walks through the heap and checks, is this actually a heap? Meaning that every node has children whose travel time, in this case, is larger. So debug check would immediately say, this is not a heap. You've done something wrong. I don't know how you got this in here. Again, that can't happen if your code is correct. If you use the priority queue or the heap correctly, that will not happen. But if you have bugs, that can happen. And it's kind of a difficult thing to find. Debug check can find it for you. Debug check is going to slow your code down a lot because it does all this extra checking. So running it on the St. Helena map, and the unit tests do that for valgrind, so you can see how they run in St. Helena, allows you to run this on a small map if you find debug check is just slow and is kind of painful. Okay? All right, so that's about getting functionality. Then there's speed tuning. So to tune the speed of your code, you want to work, this is kind of a general principle, what you want to do when you're coding and things aren't fast enough. You want to start with the algorithm, because that's usually where you can get the biggest bang. Then you think about the data structures. Are you storing things well? And then finally, you think about low-level code. So, yeah, so just attack it in that order. It's hard to see large amounts of data in the debugger. So I'm recommending that you actually watch your algorithm run on some of the simple test cases where you can, single step and see what it does. But for the large test cases, it's difficult to do enough single stepping to see that. What you can do is then use graphics to animate or visualize what's going on, which is what I was showing you with our reference solution. We can watch the algorithm and see where it's exploring. So we can actually see what our Astar algorithm is doing compared to our Dijkstra's algorithm. And it's a lot, people are very visual. It's a lot easier to do that with graphics. It's best not to leave some graphics on in your final submission. In our auto testing, we actually disable your graphics. So we have a call to turn them off. And the reason is we don't want you hanging the auto tester. So generally, even if you forget and leave visualization on, it'll be okay. But for the best safety, what you want to do is in your final submission, if your algorithm has been drawing stuff to the screen, have it defined or some other way to turn it off before your final submission so that you don't unintentionally slow down your algorithm because it's still trying to draw stuff to the screen. Okay? So what does it look like to visualize these larger cases? It's not much code. So here's the basic skeleton of the code that we're using in our reference solution. So we're including Chronos, we can get some timing functions, and we're including the threading libraries so that we can call their delay functions. Okay, so we include a couple things. I'm defining a preprocessor variable called visualize so that I can easily turn off all of this visualization code when I submit so that I'm not going to slow down my code at all, for sure. And so inside this compiler guard, basically, this will be inside the wavefront expansion, the kind of inner loop of my algorithm. So it's getting things off the wavefront, getting nodes off the wavefront, and looking at all their outgoing edges or street segments. And if I want to draw those street segments, I just need to get a renderer. So I can ask EasyGL to give me a pointer to a renderer. And then we've made a little helper function saying highlight street segment. So this just basically draws a certain street segment in whatever color we ask for. So in our reference solution, we're drawing that in blue. We want that to show up right away. So we don't want to wait for user input. We need this to show up on the screen so we can actually see the algorithm in kind of real time. So we call this flush drawing. If you don't call flush drawing, the graphics library is allowed to just buffer up the requests for efficiency. It can wait until basically you stop doing things and you're waiting for user input. We don't want that. We actually want to see the animation. So we call flush drawing. And then we actually need to slow things down. If we actually do this without somehow slowing it down, it draws fast enough that it's hard for us to follow. So I'm going to call this delay function, which is a helper function I've written down here, to delay I passed in the number 50, so 50 milliseconds. And obviously, if this was too fast or too slow, I'd say change that number. So this is a little helper function called delay that I wrote here. So all it does is basically take in some number in milliseconds and calls chrono to turn that into a chrono object that represents 50 milliseconds. And then we make a call to put our current thread. So that's basically our current program, right? The program that you've written so far for almost all of you is single threaded. meaning there's just one thread that is what is your program doing, and we basically say go to sleep for, in this case, we're saying 50 milliseconds. Go to sleep for 50 milliseconds means just don't do anything for 50 milliseconds. The operating system won't give you any CPU time. You'll just sit there. And that is enough to slow down the graphics so we can see what's going on. Okay. So this is, it's not a lot of code, as I said, to actually be able to visualize your algorithm. Okay. The other thing you can do if your code's not fast enough is profile it. So we went through in tutorial 8 how to profile your code. We showed you that you can get visualization output in a couple different ways. One is the call graph, the other is the flame graph. Here's the flame graph from our reference solution. So it basically says the public performance test. This is basically a bunch of test setup code. And that test setup code calls a bunch of setup functions. And eventually we start calling find path between intersections, which is our find path functions, which calls the Astar version of it, because we wrote a few different versions. And now the interesting part is, well, where does the CPU time go in the helper functions? Okay, so a lot of it for us is in the priority queue. A bunch of it is in getting info about street segments and so on. Okay. So we have some time in our priority queue, some time in getting information about the street segments, finding what's connected. So what are the next set of intersections that I'm going to get to, and doing turn computations. So this can be helpful to find bottlenecks in your code that you might want to speed up. Okay, so that was all I was going to say about milestone 3. Actually, let me give you one last tip, which is so I said start with algorithm, then move on to data structures, and finally you can do low-level coding. So let me tell you one low-level coding technique that we haven't really talked about but is useful. So if you have a loop like this for int intersection, let's say inter equals 0, inter less than get num intersections, inter plus plus. Okay, and then I do something. So in this loop, I'm going to go off and do something. So I just made up a random loop here that's going to go over all intersections. Is there anything I can do to speed up this code? So there is something I can do to speed up this code. It's not going to speed it up, by like an order of n or something, but it can save me some CPU time. Okay, so I've only shown you one line of code. So the only thing that you can do to speed this up is something in this one line of code. Oops, and this get num intersections is a function, sorry. Yeah, so this get num intersections is a function call. The compiler analyzes your code. If it could figure out that get num intersections, which is a call into streets database, always returns the same answer, then it would only call this function once and then store the answer and use it every time you went through the loop. But generally, the compiler will not be able to figure that out. The reason is get num intersections is off in our library. It looks at a bunch of data, and it's not clear to the compiler that, well, maybe somewhere in the body of this loop, maybe you change something that is going to make this return a different answer. But you know that this is actually not going to change in this loop. This is constant once you bring in a map, so there's no way it's changing. So if you actually rewrite this to say, num inter, okay, so int num inter is equal to get num intersections, and then you get rid of this and basically use num inter, that's actually going to be somewhat faster, okay, because I removed a function call that I was doing inside of a loop, and the compiler's not smart enough to figure out that I don't really need to do this function call every single time. I could have just stored the answer. So in this case, writing this more explicit code that gets that answer and caches it is going to speed up your program some. Okay. Is the size of a vector check as fast? The size of a vector check normally So dot size will usually be fast. So that's a good question. So if you have vector, some vector, I won't call it vector, let's call it vec dot size. That's usually going to be pretty fast. The reason is the compiler has usually figured out that there's nothing in your function that's going to change the size of the vector, and therefore it doesn't have to call that every single time. This is also a really small function, so the compiler can often inline it, meaning it'll actually paste in the code that that function uh, does. So the compiler's got a better chance of optimizing this very simple function than it has of optimizing this. But if you're worried about it, you can do the same trick, and it might be faster. I can't, the compiler tries to prove that this is not changing. It tries to inline the code, meaning it doesn't actually call the function; it just pastes the code in. Sometimes it doesn't get it perfect, so doing the same trick could help with this too. But it's definitely going to help here. Okay. Yeah, and dot size is order one, and this is order one. Okay, so we're not changing the order of either of these things. This is order one. It's just going to call a function, look up a little bit of data, and return it. But there is overhead to calling a function. And the compiler probably did not inline this, meaning take the code that implements get num intersections and stick it right into this for loop. So it might have, but it usually won't. So that is a low level coding technique that's not too hard to do and can speed your code up. All right. Yeah, and I guess Mark, you're saying the vector data type does store dot size, but basically your question, so it's going to be order one for sure. You're basically asking the question of, is it going to go off and make a function call, or is it going to be inlined? It's probably going to be inlined, so that calling vec dot size in a loop like this is fine, but it's harder for this case. Okay, because that function, it's not as obvious to the compiler that function is important, and it's less obvious to it as well of what exactly it does. Okay, so that was all I had on milestone 3. On tomorrow, we'll start talking about milestone 4, which I'm sure you guys are not yet thinking about too much, but we'll go through what are techniques for it. It builds on your milestone 3 algorithm. And I think we'll end it there for today. If there are any questions, I'm happy to stay on the line and answer them.